The elimination method is the final method we will use to solve systems. We've discussed graphing, we've discussed substitution, and now we'll talk about elimination. Graphing is nice when, number one, it's an easy graph. They give you the planes to use. Substitution is nice when a variable is isolated. However, sometimes the variable won't be set apart from everything else, so we must have some other strategy to use in order to solve. So when you think of elimination, remember we are getting rid of something. And that's what we'll do here whenever we start solving using elimination. We will actually combine the two equations, and for us, it will mostly be adding the two equations to eliminate one of the variables. Now, in order to eliminate one of the variables, either the x coefficients or the y coefficients have to be opposites. The reason they have to be opposites is because what happens when you add opposites? Well, you get zero, so something is going to zero out. So look to have your two equations where they have opposite terms. Sometimes you will have to multiply one of the equations or both of the equations, but we'll save that for another day. Right now, I just want to look at what happens when they're nicely opposite for us. You're going to add the two equations together and you will combine like terms. And when you do this, one of your variables will eliminate. It will cancel out. I prefer to say that it will zero out. You'll see as we get there. So you'll be able to have one variable with one equation, a very simple one-step equation, hopefully. You'll solve the new equation, and then you'll substitute to get the other variable. You'll write the order pair, and please remember, you always want to check your answer. Let's look at number 1, shall we? I notice that I have two equations, and I see that I have a y and a negative y, and I'm still using my same process here of labeling my equations. See that these are opposites, so when I add those will zero out. But if we add the y terms, we have to add all the other terms. So what happens when you have x plus x? Well, the result is 2x. And the sum, 7 plus 9, is 16. Now I have a one-step equation. If 2x equals 18, then x must equal 8. I know what x is. Now I need to find y. And in order to do that, remember, I look for the simplest equation, and it appears to be equation A. I must substitute x equals 8. So my new one-step equation is 8 plus y equals 7. And in order to solve that, we will subtract the 8 from both sides. We find that y equals negative 1. So it looks like my ordered pair solution may be 8, negative 1. So let's see what happens here. So when I have 8 plus y, or x plus y, does 8 plus negative 1 equal 7? Yes. And when I have 8 minus negative 1, I hope I get 9, and I do. So guess what that means? That means this is the right answer. When I look at number 2, I see that I've got the x's as opposite terms now instead of the y terms. But I still use my same labeling. And now when I add, my x terms will eliminate. When I add 3y plus 2y, I get 5y. 7 plus 13 equals 20. And to solve this, we divide by 5. We find that y equals 4. Now I'm going to substitute into one of my two equations. I believe I prefer equation A, where 4x plus 3y equals 7. So 4x plus 3 times 4 equals 7. Now I have a little two-step equation, but that's okay. We're comfortable with those now. I'm going to subtract the 12 from both sides. I find that 4x equals, oh, that was almost a bad thing there. Good catch. I find that 4x equals negative 5. And in order to solve for x, I must divide both sides by 4. And I get a fraction, but you know what? That's okay. So I believe my solution is going to be, now be careful here, I've been known to transpose the two. It happens. X is negative 5/4 in this problem, and Y is 4. So let's check this to make sure that we've done everything properly. I'm just going to jump over this for a second. So I have 4 times negative 5/4 plus 3 times Y. Please get 7. I got 7. I'm going to take negative 4 times negative 5/4 plus 2Y, and I should get 13. And I do. So guess what? This is the correct solution. And that leads me to number 3. When I look at problem number 3, I see that my Y terms are opposites. So this is equation A and this is equation B. I add the two equations. 5x plus 3x is 8x. Negative 2y plus 2y will zero out. 9 plus 7 is 16. And so we have the equation 8x equals 16. If 8x equals 16, then that means that x equals 2 because we divide both sides by 8. And so now we have to decide or calculate or find the y value. So I'm going to substitute into equation A. So the equation is 5x minus 2y equals 9. Now, a lot of you would not rewrite the equation, and that's okay. I just do that so that I make sure that I'm substituting into the proper place. So 5x minus 2y becomes 5 times 2 minus 2y equals 9. So if 10 minus 2y equals 9, we will subtract 10 from both sides. We find that negative 2y equals negative 1. Dividing both sides by negative 2 yields, 1 divided by 2 is 1/2. Since we're dividing negative divided by negative, we keep our positive answer. Remember, anytime you divide numbers with the same sign, the final answer is always positive. So I think my solution will be 2 1/2. So let's see if that works. I'm going to take 5 times 2 minus 2 times 1/2, and I should get 9. Yes. And I'm going to take 3 times 2 plus 2 times y, and I should get 7. And I do. So guess what? This is the correct answer. So these are really nice whenever you have opposite variables that you're studying, because remember, once you add opposites, they're going to zero out. But sometimes you're going to have problems where everything zeroes out. So we've talked about no solution and infinitely many solution. We talked about them in terms of a graph, and you also saw them in substitution. But since this method was pretty straightforward, I thought I should use this time to elaborate a little bit on special solutions. No solution occurs when all the variables zero out and the remaining equation is false. So that will happen in a problem like this one. So we see that the y's are opposites, so we're going to start adding. But I noticed that 3x and negative 3x are opposites. We said y and negative y are opposites, but I still need a placeholder down here, and that placeholder is going to be 0. However, when I add negative 4 to 12, I get 8. So I get the statement that 0 equals 8, and we all know that that is false. 0 will never equal 8, no matter what you do. That means that this system has no solution. There is no ordered pair that will be true for both equations at the same time. And that's actually what I should say here. There is no ordered pair that will be true, or, we say that will check both equations at the same time. Okay? Remember, whenever we graphed it, we got parallel lines. So keep that in mind. Infinitely many solutions. That occurs when the variables zero out and we get a true statement. So when we add here, 2x plus negative 2x is 0. 4y plus negative 4y is 0. So we have 0 on the left side. But at the same time, negative 8 plus 8 equals 0. This is a true statement. So this has infinitely many solutions. Please note that infinitely does not have an A in it. I like to just abbreviate this IMS. That way we don't have to worry about any spelling errors. Now what happens here is there are there's an infinite set of ordered pairs at work. Oh, my bad. There are many ordered pairs that will be true for both equations. Simultaneously. Remember, that's just fancy for at the same time. And this graph will have, they call them coincident lines. They're just the same line. They're just traced on top of each other whenever you graph them. So let's just summarize everything here. Sometimes you do have a special solution of no solution or infinitely many solutions, but that happens whenever we eliminate one variable. We will zero out one variable, solve for the other, substitute this back into one of the equations, and solve for the second variable. So when you are using elimination, you are looking for opposites. You add the equations, and you're only messing with one equation now. But always remember, check your answer.